Go. Okay. Good evening, everyone. My name is Royal Sequeira. I'm a machine learning developer at AISC Support. And today I will be presenting Ernie 2.0, a recent addition to papers written after Sesame Street characters. So this is a paper by Baidu Group. And I would like to thank the authors who spent their time helping us understand some of the parts in the paper that we had trouble understanding, and they have been also helpful replying to our emails and answering our questions. I would also like to thank Rahela and Gordon for facilitating this session. Uh, all right. So what are the main contributions of this paper, right? Ernie 2.0 provides a framework for continuous incremental multitask learn pre-training. So that sounds like a mouthful, but I will eventually get into what these words mean. And the other contribution is that it outperforms on BERT and ExcelNet on 16 different tasks, including Glue for English. So one of the major motivation behind this paper is quite a lot of existing language representation models like GLOW, BERT-OVEC, or BERT even depend on co-occurrences of words and sequences. Whereas Ernie 2.0 incorporates a rich variety of syntactic, semantic, and lexical features to sort of learn to represent the language better. And the other, I think the major contribution of this paper is that you can add a new task anytime during the training process to sort of learn to improve the language representation. So just a little bit of background here on multitask learning. I don't know what happened with the slides there. Uh, so multitask learning is basically learning to represent language based on a lot of data across different tasks. So here you see there's task 1, task 2, task 3. There are 3 different tasks. Task 1 could be something like sentence classification task, like sentimental analysis, right? Task 2 could be, let's say, text similarity. Given 2 sentences, you would want to find the syntactic similarity, semantic similarity between 2 sentences. Task 3 could be text pair similarity, a text pair classification. That is, given 2 sentences, you would want to find you would want to recognize the textual entailment, right? So in this, there is a shared encoder, and the shared encoder is used to represent the input sequence as such, and this shared encoder is common across tasks. So you might see these broken arrows in here. So the way it essentially is trained is you have the input sequence. This input sequence is represented through shared encoder. And let's say in first step, you use the task 1 architecture. Let's say sentimental analysis. You learn sentimental analysis task here. And based on the loss, you update the shared encoder. In step 2, you might use the shared encoder to learn task 2, and so on. So this is one of the ways to do multitask learning. But the problem with this approach is the second time when you are eventually when you use the shared encoder to learn your task 2, task 3, and so on, you are forgetting whatever you have learned in your previous task. So that is called catastrophic forgetting. In contrast to catastrophic forgetting, if you could learn a new task and remember what you have learned, just like human beings, right? You learn how to skate, and when you learn how to ski, you don't forget how to skate, right? So that is called continuous learning. That is, when you learn a new task, you don't forget whatever you've learned on previous tasks. But then this approach that I was explaining earlier, you might forget. There is catastrophic forgetting in this kind of approach. So what Ernie 2.0 does slightly differently here is, let's say you have task 1, you have the input sequence. With the shared encoder, you learn this task 1, and then based on your loss from task 1, you update the weights of the shared encoder. And then when you have task 2, instead of beginning on with task 2 totally differently, you have task 1 and task 2 learned at the same time. That is that clear? I can explain it better. So you have the same input sequence, let's say. So you have an input sequence, and you train task 1 on GPU 1, and then GPU 1 has its own data, and then you compute the loss corresponding to this task from that GPU. And then when you learn task 2, you also compute the loss corresponding to that task from the other GPU. And if you have another task, let's say task 3, you also learn the loss corresponding to this GPU. So essentially the difference here is in the subsequent steps, you're learning 2 tasks at the same time. In the third step, you're learning 3 tasks at the same time. Yes.
Does it happen for batch? Like every batch of data,
yes.
You have you add the gradients together to update the weights?
Yes. Yeah, so this happens at a batch level. And so based on the batch, you calculate the average loss, and based on the average loss, you update the shared encoder. Is that clear? Yes.
What is this task 4 that you did not know about and came out a month later, and you want to train it on task 4 as well?
Mm-hmm.
So is that accounted for?
If you want to learn task 4 after this, so you would have to start from the beginning again. Like you have the shared encoder learned on task 3, but now you have the you don't begin from scratch. Like you have shared encoder learned on task 1, task 2, task 3. So now you begin with task 1, task 2, task 3, and task 4.
Yeah.
Okay.
This is what they mean by the sequential learning. So you're sequentially adding a new task in each iteration. So if you have a new task 4 that you want to add, you add that and train 1, 2, 3, 4 simultaneously.
So it doesn't change when, like, if you change the order, basically, like.
That's a good question. I think we will come to that maybe in the discussion points. But at the moment, the way I forgot to mention this, the way Ernie 2.0 does training is you begin with the easiest task. You initialize, like your task 1 is the easiest task, and then you gradually increase with other tasks.
So how do you define what's easy?
I think they just say they begin with knowledge masking task. The word masking task that I'm probably because Ernie 1.0 did it too, and then that's what they begin with. And they just mentioned that that's what they begin with.
Do they start the shared encoder? Do they start with fully training it with task 1, and then they add task 2 by running again with task 1 and task 2,
Yes.
and then 1, 2, 3, and then like 1, 2, 3, 4?
Yes, it's fully trained.
So basically, if we have 7 tasks, it's gonna basically be 7 cycles of training.
Yes.
Starting from 1, then 1, 2, 1, 2, 3, 1, 2.
Yes, that's
okay.
correct. That's correct.
Can you take a question from online?
Yes.
Can these tasks be performed with a single GPU?
Sorry, guys, please.
So if there are 3 tasks, each task are on each GPU. So they cannot be performed on a single GPU. Right.
I think it's possible if you do one batch for task 1 and wait and have that, keep that loss and do that. It's gonna take longer only, yes. So in this case, it's quite clean and clear that you have one. Oh, sorry, this was the online question, yeah. So I think it's still possible to do it. It's just gonna take a while because you have to wait until task 1 is done and then upload your batch for task 2 and then.
Okay.
Any other questions?
Yes.
Yeah.
Also online, how to determine the weight of each task in the average loss?
There is no, do we do weighted average of loss?
The weight of each task in the average loss. So it's like a weighted average, like weighted loss.
Yeah.
A sum of loss.
Yeah, so I think we sort of asked this to the authors too, but the idea was you just average the loss equally weighted. The reason is, maybe I can clarify it a little more, because one of the explanation for this is, let's say you have your shared encoder, you have already learned, in the first step, you already learned your task 1. In the second step, your shared encoder is not really updating as much, or your losses are not really changing as much for task 1 because you've already learned to represent for your task 1. So it's mostly changing with respect to task 2. Yes.
So in a mathematical term, basically, let's say if you, from the beginning, you know that you're gonna do it for 7 tasks, so you just write down the whole thing, and then at the beginning, all the weights for the 6 last ones are 0, right? And then start from 1, and then, right? So, but what's the definition of convergence in this case then? Basically, when you stop, you say, okay, I'm done with the task 1, and then I'm gonna go to task 2, right? Because you can't continue forever.
I think the trade-off here is because you're using multitask learning, which the major advantage of multitask learning is to sort of serve as a regularization function, right? You would want your shared encoder to generalize to all different tasks. You wouldn't want the encoder just to work well for sentimental analysis or sentence classification. You would want it to work across the tasks. So there is a trade-off. Although, like, you might have converged in step one, but then the essential detail, like the essential constraint here is that the encoder would have to work across the task. So you would have to like retrain it.
I have a quick implementational question here. So how do you, where do you gather the gradients, in a separate node or in one of the nodes? Like how does it work? Because there are some methods to speed things up when you want to parallelize across tasks like this. I just want to know how they approached it.
Unfortunately, I don't know the implementational details because this code is also written in paddle.
Yeah.
So, but I don't know if the facilitators, I think, yeah, it's pretty much, we don't really know. The idea that we have is based on the average loss across. Maybe there's like a master node that collects all the loss and then updates the shared encoder.
So just to say that the only reason I mentioned is that sometimes, given your task and the parameter size, some part of your network may finish their job earlier, and there are methods to make sure that won't stop, that won't become the bottleneck.
Right. Yeah.
Right? But we can discuss that in the discussion.
Yeah.
Thanks very much.
Okay, so this is the picture that they provide in the paper. It was sort of confusing for us to begin with. Basically, what they're doing is you construct the task, which is mostly like building the weekly supervised data set, and then so task one. So sequentially, here is. So okay, anyway, so sequentially here is, so you have task one, and then based on your task one, the shared encoder is updated, and then you have task one, task two. So this is essentially, that is the arrow that sort of demonstrates that task one is used to, sort of sequential multitask pre-training, and then task one, task two, and so on.
Fine tuning.
Oh yeah, and then finally, once you have this Ernie model trained, you can use it for your fine-tuning. You can fine-tune it for downstream tasks like sentimental analysis, question answering, text similarity, and so on.
And what is prior knowledge here?
So the prior knowledge is mostly things like Baidu's search engine log, and then Wikipedia text, and like text from different sources. And then based on this source, you construct different tasks, which I'll be explaining in the next few slides.
So you're going to go deeper into
mostly the task construction and so on.
Okay, could you walk me, because I wasn't in the circles like that, but could you walk me through again?
So initially, based on, let's say, Reddit, book corpus data, and so on, you construct different tasks, which I will be explaining in the subsequent slides. And then based on those tasks, you pre-train your model, like I was explaining earlier. So you have task one, and then using the task one and the shared encoder, based on task one, you learn your shared encoder. Next, you have task one, task two. That's what the sequential here means, and then so on until task one to task n.
Will you explain how they prepared the input? Did they augment the text? Okay.
Yeah. So I will comment. I will talk about constructing the tasks and individual tasks and so on. Okay. So this is sort of the architecture that looks like. So at the very beginning, we have task embedding, and task embedding sort of modulates the subtleties pertaining to individual tasks. So let's say if you have sentence reordering task, and I will also be explaining what these individual tasks are later, but let's say if you have sentence reordering task, you have an embedding specific to this task. And then upon that, we have position embedding. So position embedding is, because we are using transformer, it's not like a bi-LSTM network, right? So all these tokens are represented parallelly. So you would need a position embedding for each token. And the other thing that position embedding does is sort of captures the importance of a position. So if you had a sentence like Jason kidnapped Jeremy and Jeremy kidnapped Jason, like these two are totally different. Like the position of who's where also matters, right? So position embedding sort of captures that as well. And sentence embedding is to sort of demark your sentences. So A is here, A here means the first sentence, B means second sentence, C means third sentence, and so on. And then finally, we have the token embeddings as such. So you have token 1, token 2, token 3, and then separating token basically indicates that that this sentence is separate from that token. It's sort of like a sentence marker, just like sentence embedding. And then the CLS is the embedding to. So you use it for sentence classification tasks eventually, but it also sort of represents the whole sequence as such. I think one small detail here, we have sentence embedding. Why do we also need a separating token? It apparently helps in converging faster if you have both these details, I think.
Any questions?
So,
The task embedding, is it learned or it's just a fixed vector or what is?
At the very beginning, it's randomly initialized, but I don't know if it is updated. Probably is updated during the process. No.
My understanding was that it was just fixed.
Yeah.
Yeah,
Okay.
so it's
Me
just
too.
if you're performing task 4,
Yeah.
the embedding is just 4, or some indicator for 4. Hassan, you had a question?
It's probably just me not necessarily not listening well, but you had a separate token. Did you say? So you're separating sentences, or?
Yeah, you're separating sentences. This is one sentence, second sentence, and so on.
Gotcha. And CLS, you say, was the tasks class?
So so CLS usually is used to classify the whole. So this represents the whole sequence, and then this is used for sentence classification tasks.
Isn't CLS to indicate the start of every sequence?
Yes, but it
It's
also
always this first token of a sequence.
it's first token of the sequence that is used for things like sentence classification. Yes.
I think this might be good for the discussion part, but I wonder if the task embedding is fixed, would it make a difference in terms of a task-specific classification at the end? I mean, if it is fixed, then what difference would it make?
One thing that the paper does mention is when you use for do you mean like downstream tasks, like name entity recognition and so on, right? So they say you can use any task embedding to begin with to fine tune. It doesn't matter what task embedding you initialize with. And this is
Before you move on, so your CLS, is it the same across tasks? Is it because what is a sentence class?
So it is per class. So per sentence, right? So this CLS token is eventually learns to represent this input sequence.
Per instance, you get an overall general representation of the whole sequence. So for downstream task, you can just use that vector instead of trying to max full or average all the vectors of each token.
You could sort of think of it as like a sentence embedding.
And the same
exact same thing that Bert did.
Okay.
And I think that they might even feed the actual class in that 0 position.
Mm-hmm.
So.
Okay, nice.
Any other questions? So this is the loss in Ernie. So it's basically this image compressed. So you have the tokens, then the tokens are represented through encoder, and these are basically the output of the encoder. And you see multiple losses here. It basically means it's the same architecture run on different GPUs, right? So if you're predicting something like name entity recognition or knowledge masking task and so on, you can have token level losses. And if you're depending on this token level loss could be coming from GPU 1, that could be coming from GPU 2, which is running a different task and so on. And then the sequence level losses are based on your sentence classification tasks and so on.
Shouldn't it have one layer on top of it that connects everything? Then it wouldn't be so confusing. Like the average, what do they do with all those loss functions? I was looking at the picture and I was confused. So what do they do with it?
Slightly confusing.
Right?
They took out so many of the parts of the network.
Does it make sense if just all of them go to
one final loss per batch?
Yeah.
Yeah, they never really visualized the aggregation of the loss from the different networks.
Yeah.
But but that is still what's happening. And I think when you see loss 1, loss 2, loss 3, that's for each different task. That's right. And the V's here are the output vectors at each token position in the final layer of the shared encoder.
So, like, when we have so many tasks, right, and like dedicated GPUs, so how does the stochastic gradient work for this? Basically, like, you go through all the data for all of them, and then you like take one step, or basically you have, I don't know, like combination of all of them, and then one step, and then basically new data from each task. How does it work?
Good question.
Yeah. So you basically one thing is you have same data for several tasks. So let's say if you have same data for several tasks, you calculate the loss for that mini batch. So you have a mini batch. You calculate the loss for this mini batch from, let's say, GPU 1, and then you wait until GPU 2 is done getting its loss, and then GPU 3 and so on, and then you average the loss across the batch, and then you use that loss.
Share the input, right? They share the input.
They share the input, but there are also 2 tasks where they don't share the input, and our understanding is that they just do an average as it is. So for like most of the tasks, they share the input. They have the same input, but there are also 2 more tasks where they don't share the input.
Yeah, we'll see once we get to the data sets, you'll see which inputs are shared across which tasks and which ones are specific to which tasks. But nonetheless, the losses all get averaged together.
Yeah.
So both the token losses and the sequence losses get averaged, and you have one loss where you compute the derivatives
per batch.
So for all the token losses, because your token losses, you average them anyway. So you have the average token loss, and then you have the
You add the token loss, the average token loss, to the sentence loss per instance, but you average over each batch.
So per instance, you have the sentence, like Rahela was saying, the sequence loss, and then you get all the average token losses, and then you sort of average this loss across the instances to get the batch loss. Gotcha. And then, like Gordon was saying, so these are the 2 IR relevance data and discourse relation data are the only ones that are using 2 different data sets, but otherwise encyclopedia, book corpus, news, and dialogue use. I will explain these tasks in detail. But
what is instance?
Instance is the sentence, or like a sequence. And a batch can have, let's say if batch size is 16, you have 16 instances. So,
okay. Sorry, one last question, then we can move on. Are there separate layers dealing with each task?
Separate layers. Do you mean like, okay? So is the architecture same across? So the architecture is same across all the tasks, and that is mostly because all the tasks are classification tasks. I'll also explain this in the subsequent slides. But it's basically the same for each task.
Separate networks on top of the shared encoder, but they have the same architecture, like the same number of layers, but they are separate.
So basically, no. If they say that, I see, like, for example, like Elmo would say that the first layer is good for POS tagging, the second is for, I don't think that, no, they don't, like, they took the output, which is, if it's base model transformer is 12 layers, you took the output at the last and use it for the pretraining tasks. You don't take the middle way output vectors.
Okay. Any more questions? Okay, so finally, the set of pre-training tasks. So there are 3 kinds of pre-training tasks: word-aware, structure-aware, and semantic-aware pre-training tasks. Yes?
Sorry,
no problem.
Just a comment.
Yeah.
So it doesn't make sense that they have the same architecture because we have different outputs. So they cannot have the same architecture. You have the transformer, and then the upcoming layers, they can't have the same architecture.
Yeah, but
we're learning language representation, which makes sense. I mean, you can fine tune the other layers later on for specific tasks.
I think when I say same, we had the same discussion too. And then when I say same architecture, the softmax or the final layer might change, but like overall, it's this, like the number of layers or number of hidden layers and so on would all be similar or same. So word-aware pre-training task. So in this task, basically the model gets to learn to represent word better, or sort of gets an understanding of the word better. And the first task they have is knowledge masking task. It's similar to what BERT does too. That is, you randomly mask a word, and then you predict the word. This is also a classification task. Basically, so in this example, James was masked by Jeremy. You're trying to classify this masked word in the vocabulary size. So it's the vocabulary size classification problem. Something that they do differently here compared to BERT, but inspired by Ernie 1.0, is instead of masking just words, you mask named entities and expressions or phrases together. So like mask was written by George R.R. Martin. This way, if you're masking like the entities together or phrases together, the model can know that, oh, this is a named entity in some way, or it sort of learns the global and local context of the words better. So that's the knowledge masking task. The second task is capitalization prediction task. So this is also a classification task. So given an input sequence, for each word, for each token, you would want to predict whether this token is capitalized or not. This is an important feature. Let's say by knowing that, oh, this word is capitalized, the model gets to know that, oh, this must be a named entity, because there's a very positive signal that if a word is capitalized, it must be a named entity. So it could be helpful for downstream tasks like named entity recognition. The third task is token document relation prediction task. So let's say you have a sentence like this: a meme is an idea, behavior, or style that blah blah. So given this segment and given the original document and several other segments, the task here is to given each word in this segment, let's say you would want the model predicts whether this word appears in other segments elsewhere in the original document. Is that clear? So if a document is written about memes, and then for each word you try to predict whether this word appears in other segments in the original document. So that way the model sort of captures the theme of the document, and it also sort of knows whether this word is important or whether it's a keyword to sort of capture the meaning of the original document. Is that clear? Okay. So that was about the word-aware pre-training task, right? So now we have structure-aware pre-training task, which is you would want to get a sense of this paragraph or like a document, sort of a higher level understanding. So in the first task is sentence reordering task. That is, given a paragraph, you break this paragraph into, let's say, m different segments, and then you reshuffle them. The model has to reorganize these sentences. So this also can be termed as a classification problem, wherein given an input sequence, segments of input sequence, the model tries to say, oh, whether this is the original sequence or not. So the permutation here, let's say all randomized could be like one permutation, and the original segment is like another permutation. So you're trying to predict whether, by reorganizing the input, the model is trying to, it sort of understands the structure of the paragraph or sentence as such. Yes.
Does the model know into how many pieces did you break the sentence?
I think so, yeah. I mean, it would have to know.
It can be like up to m pieces, right?
Yes.
So how is that structured? Like,
I think only by knowing m and therefore calculating how many classes it could have, it can do the classification problem. So I think the model should know how many pieces the sentence is segmented into.
Isn't that what the SEP delimiter token is for? Like the SEP basically divides the document into individual sequences, right?
Right.
Subsequences. So isn't the model aware of the position of the separated token? So based on that, it knows that, okay, this is where the sentence ends and the next one.
Yeah, that is possible. Yeah, I think that's very valid too. Yeah, based on the separating token, it can probably count how many. But I think the problem there is, what if the sentence as such has a separating token? Like this is a paragraph, it could inherently have a separating token too. But yeah, I presume the model would be aware.
So I think the paper mentions it's broken down per paragraph. They actually divide into paragraphs and then apply the model the sentence task.
Yes.
So how do they structure this task? Basically, like you have different permutations, and you say like basically true or false? Like, is this like meaningful or
it's a classification task. So you would want to predict, whether this is given a segment, you would want to know whether this is the original segment. So the original segment would be one class, and then reshuffled classes would be other classes.
Basically, kind of like true or false, right? We're gonna have several true falses and then one true.
Yes, yeah.
So like maybe like some of those permutations are like meaningful, like maybe in some sentences like doesn't matter.
There could be equality, yeah.
Independent, right?
Yeah.
So, anyways.
Yeah. Okay. So any other questions? Okay. So the other task is sentence distance task. That is, this is also a classification task. So given two sentences, you would want to know whether two sentences appear in the same document or they appear in different documents. And if they appear in the same document, do they appear next to each other? So the model would have to understand these sentences and then sort of know whether could they appear next to each other. So if they are adjacent to each other, then it gets a label of 0. If they are in the same document, then 1. And if they are from two different documents, then it gets like labeled 2. So this is sort of treated as a 3-class classification problem. The other pre-training task is semantic aware pre-training task. So here, the first task is discourse relation task. That is, given two sentences, something like, or like given this sentence, I took my umbrella this morning because the forecast was rainy in the afternoon. So the discourse here, the discourse marker here is because, and that is the task, to predict the discourse marker. So by learning to predict where the discourse marker exists, the model sort of gets the semantics of two different sentences. That is the task. So that is discourse relation, and then the second task that they have is IR relevance. So this is also a classification task because each token could be like it's from the it could be a vocabulary size that you're trying to classify whether a word is a discourse marker or not. And the final task is IR relevance task. So this is based on Baidu search engine logs. So let's say given a user query and then a document, you would want to predict how relevant this document is to the user query. So the proxy that they use is if the query words appeared in the document title and then the user clicked on the document, that indicates strong relevance. If the query words appeared on the document title, but the user did not click the document, then that indicates weak relevance. And if the query words did not appear in the document title at all, then that indicates irrelevance. So by trying to predict, basically here the model would have to understand the semantics of the query and the document before deciding whether it is a strong relevance, weak relevance, or like irrelevance. Is that clear? All right.
So do they use a information retrieval dataset for that?
They use Baidu's search engine logs. Yeah. So, okay, so we will take a quick break now, and then reconvene to discuss experiments and results after.
All right. So yeah, it'll be about 5 minutes. Feel free to get some more pizza, use the wash.
Okay, no problem. Okay, so experiment section. So they run their experiments on English and Chinese. English, they use Wikipedia, book corpus, Reddit, and discovery data. So this discovery data was used for the discovery relation task that I was talking about earlier. And for Chinese, they use data from Baidu search engine log, and this data had data corresponding to news, information retrieval, encyclopedia, and so on. So because they compare Ernie 2.0 model with respect to BERT, they have similar settings as BERT settings. So they have BERT base, Ernie base model and Ernie large model just to compare with BERT base and BERT large. And for fine tuning for English, they use GLUE. So GLUE is basically the standard set of evaluation for natural language understanding. And then GLUE has various set of tasks here. So if you see COLA, it's like syntax acceptability task. And then there's like sentence classification, like SST2, which is sentimental analysis. There's also natural language inference, like MNLI, RT is recognizing textual entailment, There's also like paraphrase detection, like MRPC, which is a paraphrasing corpus from Microsoft. Yeah, so those are mostly the set of tasks that they use in Glue. And for Chinese, they have 6 different tasks. Machine reading. Yes.
Quick question about Glue. So, will they? Is it the case that they use these deterministically, then use the labels to train? Is that what's happening?
No, so they use Glue dataset for fine tuning. So just to back up a little bit, they pre-train the Ernie model, and then the Ernie model, once the Ernie model is trained, after let's say for 7 different tasks, right? So once you're done training for sequentially all 7 tasks, then once the model is trained, they fine tune on each of these individual tasks. Cool. So the pre-training tasks for Chinese, it includes data set from reading comprehension, named entity recognition, natural language inference, and so on. So the machine reading comprehension has 3 different data sets, and then they consider them as individual tasks as well. So in the statistics too, they say, oh, we trained on like 7 or 8 different tasks for Chinese. So those were the experiments details. Do you guys have any questions regarding these? So the paper has details about learning rate and so on, and they also say they trained on, I think, 64 V100s for English and 48 for, or like the other way around. But yeah, quite a lot of.
I remember like the learning rate was different from Chinese to English. I was wondering like if there's any specific reason.
Could you repeat the question?
The question is the learning rates were different from Chinese to English, and was there any difference? I'm not too sure. It's probably the case that that learning rate turned out to be good for Chinese than English, I think. Yes.
What order of compute power is required for initial pre-training and fine-tuning?
They don't mention the compute power for fine-tuning, but for pre-training, they use 64 V100s on, I think, English and 48 on Chinese. So
64 for large and 48 for the
base model. Okay, yeah, 64 and 48. Should I repeat that? Okay, so they use, the question was what sort of compute power is needed for fine-tuning and training, pre-training. The paper doesn't really mention, as far as I know, doesn't mention anything about the computation power for pre-training, for fine-tuning, but for pre-training, they use up to 64 V100. So I think 48 for base model and 64 for large model. Okay. Any other questions? All right. So the results. So luckily, Ernie 2.0 performs well across all tasks. So otherwise, we wouldn't be presenting this paper here, I think. So it has state-of-the result for all the tasks in Glue, and it obtains 3-point improvements on Glue score. The two major improvements that I want to point out is recognizing textual entailment. So they have 10-point improvement with respect to BERT. So the last column, 70 and 82. And then 8-point improvements with respect to AX. That is the linguistic analysis of models. It's one of the tasks. So they have 8-point improvements here. With respect to Chinese, they say with respect to BERT base that there is about 2-point improvements across these tasks. And also they say that they achieve state-of-the-art results across all the tasks. And mostly these are the tasks that achieves about 2-point improvements on these particular tasks. And with respect to Ernie large, these are the set of the tasks that also has like about 2-point improvement. I think that is all about the results. Do you have any questions about the results?
Sorry, when you compare, is it like
BERT base?
Ernie multitask versus
BERT base and BERT large, yeah. Sorry, Ernie. So in this Chinese tasks, you compare BERT base and Ernie large, and Ernie base and Ernie large.
So they don't compare Ernie. I'm just wondering if you if you evaluate Ernie trained multitask or just because we want to see the effect of multitasking here, right?
Yes. This is multitask learning. Ernie 2.0 is the multitask pre-training.
Okay. I was wondering if they could.
Good question. So I think it's asking if there is any ablation studies where you would actually see this much is due to the multitask.
Oh, right. Sorry. Yeah. So that's also, I think, one of the discussion points that.
Power of change. I don't know. The data have changed.
We spoke to the authors about this, so they didn't publish any ablation studies in the paper, but they are currently working on some.
Yeah.
And actually, we want to talk about this in the discussion, so we'll get back to it. Thank you.
Yeah.
Quick question.
Yes.
Does it mention anywhere how many parameters the model has?
I don't think so. I don't remember reading it in the paper at all.
I would guess it's
BERT, I think large.
probably the same around this. Yes, exactly.
Because it's the similar setting, it probably is.
Shared encoder.
Based on the different token embeddings and all the other stuff they stack on top of each other.
Yeah, I think there's only task embedding, right? Because there is position embedding, sentence embedding, and everything else is same as BERT. There's only token embedding at the very beginning.
And you don't update
task embedding at the very beginning.
I don't think so. Okay. The whole encoder is fixed. Yes, the same as BERT. Yeah.
Yes.
A question from online. Is there a final task that we care about that is different from all these pre-training tasks? Or is every task we care about in the end also participating in the pre-training?
I think the major motivation is to use the pre-training tasks so that you can represent this encoder, or you can better represent the language better. So you can have a better natural language understanding model. So I think in the end, using this better representation can get you scores across, like better improvements across the board. So if you were only focusing on one particular task, I think it is easier, for example, let's say, to get probably better improvements than this on SST2, but it's harder to get improvements across the board, and that's why like multitasking is important. And it probably is not that important to perform as well on the, like if you were to choose one or two, it's not that important to perform well on the pre-training task.
I think there were some tasks that were evaluated at fine-tune time that were not a part of the pre-train. So I'm pretty sure.
Yeah.
Sentiment analysis, yeah, definitely natural language inference. Though that's part of the GLUE benchmark, but it's not part of the pre-training.
Yeah.
So yeah, there were some differences.
Yeah. Should we?
Okay.
Cool. Okay. So key takeaways. One of the key takeaways is that, of course, Ernie 2.0 performs really well on across English and Chinese tasks. But the major takeaway here is that Ernie 2.0 provides a framework where you can add tasks incrementally without having to forget your representations in the shared encoder. So I think that is the major takeaway from this paper than anything else. Okay, so discussion points. First question, is this approach scalable? That is, if you were to add like more tasks, you would have to begin again with, the model would see all the data again, over and over again. Is this a scalable approach? Can we, so that's one point. Should I just go through?
No, let's pause.
Okay, sounds good.
So I think I have a comment on that, because you ended with the claim that it doesn't fall for catastrophic forgetting, but you're training everything together again and again. Like, yes. How is that actually? I know this is highly argumentative, but I was wondering if they said something to address it. Because like I could have argued that, okay, well, you just train everything from the beginning. Like, it doesn't seem to be that innovative.
Right.
Yeah, we have a similar question. So one of the main ablation studies, we want to talk about this in a second, but one of the ablation studies we would like to see is taking the approach that they proposed and comparing that to an approach where you don't do this sequential pre-training. You just take all of your tasks and train them together once.
Yeah.
And then evaluate how well that does against their approach of adding a task one by one.
What do you mean by once? Like, not do 1, 2, 1, 2, 3.
Exactly. Just do 1, 2, 3, 4, 5, 6, 7
Okay.
all at once without.
And then valid. Okay.
Because the difference here, and I think that the authors mentioned that actually in the what is the point is that when you trained already on one, you don't start from scratch. Your parameters of the encoder is updated based on one task at least, and then although you're seeing the data from task one again, but you hopefully are doing well on that. So the convergence gets faster there rather than starting from scratch with 1 plus 2.
Arguably so, right? Because you may end up in a regime which is maybe not feasible for all these languages. I mean, I'm saying I'm able to argue this because they didn't do the ablation studies.
Exactly.
If I were in their shoes, I'd probably actually argue just as you did.
Yeah.
So I understand that's reasonable, but someone like me can argue, hey, maybe that's not the case.
Yeah, and that's actually what we would like to facilitate today is maybe a discussion of, as Ro mentioned, is this scalable? This idea of constantly retraining with each task every time you add a new task, and also what ablation studies, aside from the ones we've mentioned, would you like to see to further validate their claims? So
I'm super interested to see, as opposed to training the entire thing on a new task or on all the tasks, super interested to see some way of sampling from these tasks to speed up the retraining.
Not on everything.
Not on everything. And see the results. Like if there's some way, because if you've seen something in the past, you don't have to see it entirely again.
Just a reminder.
Just a reminder, exactly.
Yeah.
Anyhow, this is a new article. Maybe we should write it.
Yeah. Yes.
I just want to make sure I'm understanding it intuitively. The reason that they do this 1, 1, 2, 1, 2, 3 is so you get closer to the a better local minimum, right? Where you instead of just starting randomly all over again, if you do that, you might hit not a great local minimum. But this, if you first get a local minimum of first task and 1, 2, so the goal is to just get to that.
Right.
Best. Okay.
Yeah. So I think what Gordon was saying was mostly the last step of Ernie 2.0, where you have all the models, but the shared encoder is randomly initialized, maybe. And now, what is the gain that you get by this approach? But I think something that Aisan was also mentioning is maybe if you were to, instead of retraining again and again, if you were just to sample it, sample the data from the earlier learned task as a sort of a reminder to sort of be in that minima, then that could help the model instead of retraining again and again, I think. Yes.
Based on the question that is it scalable or not, there is a theoretical point where you would be able to answer all of the tasks right? We're all able to do it, right? So I could understand that as you do task 1 and then 1, 2 and then 1, 2, 3, right? It might take more and more computational power, but maybe theoretically you approach a point where you do start to get the right parameters so that it does start thinking in the same way that we do. So it might be scalable in that sense.
So you're saying the convergence could be faster in some way because it's already representing language better.
Exactly.
That is possible. I think if we were to have some analysis as to how much time it takes in each training cycle, that probably is a good idea. Yes.
So the other thing I was wondering was instead of retraining the previous 6 tasks or 7 tasks or whatever, is something like freezing those parameters, is that something that might make sense? Why do we have to relearn them for?
The parameters are shared though. So if you want to be training on a new task, you can't freeze them. You need to be updating them in fact. No problem. And yeah.
Yes.
I just kind of thought what if instead of going 1, 2, 3, what if you first go instead of steps of 1, maybe do first do 1, 2, 1 and then 1, 2 and then 1, 2, 3 and then just go all the way 1, 2, 3, 4, 5, 6, 7, 8 because I'm just thinking maybe tasks 5 to 8 it might not make much of an impact as first training 1, 2, 1, 2, 3.
Spend more time in the early phase.
And just skip half of it and go straight into training the entire whole task.
Yeah, that would be another interesting thing to to examine. The one thing that we know that they are doing ablation studies for is the second point here, the order of the pre-training tasks. So the authors did specify that they are evaluating. Does it make a difference if we start with one task versus another? And so we also wanted to pose it to you guys to see, do you think it theoretically would make a difference, or what would you expect to come from that?
Just a clarification
Yeah.
question. When they compute the loss function for the additional, like when you do task 1, 2 together, do you make sure that it's the same type of tasks, right? Like a sentence-oriented task, or can you mix and match from the different tasks?
Yeah, you can combine the loss across all tasks. That's how it's set up. Yeah.
So someone brought up the point, how do we determine which task is easier and which task is more complicated? So is there any measure widely accepted in the field?
I think some tasks like machine translation, for example, is known to be harder than, I think it probably is to do with, I don't know, benchmarking on different data sets too, but I think there's like sort of general consensus that machine translation is a harder
So there is a consensus if I ask two experts to range the tasks mentioned in the presentation, there would be probably the same.
Probably roughly. There might be some
Roughly.
discrepancies, but yeah, as Roel said, machine translation would be considered much harder than binary sentiment analysis.
And you can also look at the results, like I would say, like the
In terms of
benchmarking.
how fast it trains, or
That, yes, exactly, how fast it converges, or how much improvement, like what is the final, like if we are still in the 90% accuracy in F measure, then for name entity recognizer, that's probably easier than NLI, which is like 60 or 70, I would say. Kind of.
I was just going to make a comment. I'm assuming that based on how long it takes to converge might be an indication as to how hard it is. I was curious, does anyone know if they used like a set amount of epochs or like early stopping or something like this
Yeah,
for
they
when they transfer over from task?
I think it's in the tables, yeah, that how many epochs they
How
train.
many epochs they train
In the table?
each task for.
Yeah.
Right, but I'm saying, how do they determine that?
Oh.
Like, did they, you know what I mean?
Like
No,
what
no,
is
I
the
know. I realize this.
I'm sorry, I didn't
I'm saying
understand the
like,
question.
well, did they, or before when they started off in paper sale, we're gonna train like 100 epochs this, 20 epochs this, or was it like an early stopping kind of thing and then they went back?
Yeah. I assume the number of puppy parameters are just way too much to do a great, like hard parameter search.
Yeah.
So I'm also interested to know.
Yeah, exactly.
That's what I'm saying. So yeah, like in what order, like there are many hyperparameters than you would normally have, I don't know, in a language modeling task or just a machine translation task, right?
Yeah, and I was curious too, say we just trained individually and waited till they converge, like how many epochs it would take. If we did this with already pre-trained on a previous task, like how much does that reduce, like how much transferred over pretty much?
Yeah.
Like transferred.
Great point.
Yeah.
Yeah. Great. So they didn't test it from scratch too.
I think one interesting study with regard to actually on this point was that you want to see how much multi-training is actually affecting to have better results. I think interesting data sets would be those with fewer training samples. So if you start from scratch and just one single task and try to train your network and test it, however, have a encoder which is trained this way on multitask learning and feed it and use to fine-tune that. So I think when you have very fewer training samples, then having a general encoder that's already these embeddings or the information is encoded, the information of language in general is encoded in it, helps to faster learn rather starting from scratch and not having so much label data to train the whole network. So the point, like the interesting study would be like having those data sets with fewer training samples and do single task training, starting from scratch and having Ernie and fine tuning.
So just to add to that, so in many ways they're trying to already define their pre-training objective to do better than BERT, right? Because essentially the knowledge masking is one step better than BERT because you're looking at named entities and word masking. Whereas in BERT you just did masked language modeling. And then also in BERT you did next sentence prediction. whereas here you're doing paragraph sentence ordering, which is like one step ahead of what like sentence is.
Right.
So maybe the relation study they should do is just only do those two retraining tasks because those are similar to birth.
But they also use more data too.
Well, that's a good point.
So it's like.
I mean, they use.
Variables.
Sorry, what was the point?
They also use more data. They use like separated
Right,
data on top of the.
Yeah.
I think the data is like a side effect of using more tasks, but.
Oh yeah, that's a good point.
We have the same point up here. How much improvement in the downstream tasks can be attributed to the novelty in architecture versus the size of the training data, and this is definitely a recurring question that we're having with these groundbreaking NLP papers, because each one seems to add.
They make 10 changes.
I mean, 10 changes, and some of them being architectural and some of them being training data side.
I mean, from the experimenter side, I can sort of relate to the fact that hey, I just want to be. I'm distracted because we're also picking up radio on our audio, but hopefully it doesn't disturb too much the people online. But I kind of, if I was the experimenter, I would just go aim, given how much resources I'm using, I would just aim for everything so that I can beat them with my first sort of attempt, and use everything that sort of already is a consensus in the scientific community. I know this is not the best answer, like even that I want to hear, but it seems that doing ablation studies and these are hefty thing to, like they do require some time and resources. I'm not sure even if it's even possible to answer every questions that I have. Anyhow, just give credit to the authors. And I think just trying it as the first step and then going further.
It's extremely expensive and time consuming to run any of these experiments. So
Right,
you're right. It's
also time consuming to read 10 different papers.
So I don't know what I'm saying makes sense or not, but would it make sense if you have a weighted average and then you want to learn the parameters? So at the end you look and see which task is actually contributing to the loss?
Mm-hmm.
Does that make sense?
I think.
So I don't get that. Sorry.
Instead of just averaging the loss, you have a weighted average and you learn those parameters.
Learn the weights.
Learn the weights.
Learning the weights.
But I think the point of this though is that the things that you previously trained on are gonna have like a really low loss.
Yeah.
So you're gonna do you get what I'm saying? It's kind of like innate that this one's weighted more because when you do the new task, you're gonna have a bigger loss. So you're gonna take that into account. So it's kind of the same thing as weighting that loss more.
We kind of saw it as a way of regularizing, such that as you add new tasks, you're right, you're expecting that the loss on the initial task is going to be low, but you're still computing it such that if the weights change so much that now you're not doing well on task one or as well, you still have the loss from task one to account for that or to help you bounce back.
Do you guys maybe think of this as like exploring different local minimum of the first task? Do you get what I'm saying?
I think it could be.
Yeah, that's what I wanted to say. Basically, like when you train it for another task, you're doing probably worse job for the first task, right? Because if you have done a good job for the first task, right, then like you have a good low loss, right? And then when you add another term in your loss function, then basically when you retrain, then probably you end up doing worse job for the first task, right? And the question now is that
not necessarily.
Might
Right?
just jump out.
I think the entire point of the paper is, although they've no ablation study to prove it, the entire point of the paper is the results show at least that hopefully with multitask learning you can do better. So there have been many studies where they showed working on multiple tasks will help improve the single task, and sometimes that's because the single task doesn't have enough context. So you add more tasks, you actually get more context for the first task. So that has been shown in the literature, and I think what you alluded to kind of means getting stuck in local minima. Like if you actually use another task and it becomes worse, then it probably means you were overfitting.
But like the error surface is gonna change, right?
Yeah.
Right. And then basically these are the things that they never discussed. Like in engineering papers, right? They wouldn't accept if you just like write something and then claim some stuff. But basically the question is that are we talking about the overall error surface, which is doing a better job for all the tasks, but we can't find that basically global optima if we just do it for one task. And now like we're using all the tasks kind of help to find that optimal basic point. So basically my question is that if you want to like do some task which is related, like very similar to BERT, right? And then is BERT is gonna do a better job? Does it improve basically to just like specify some tasks which is related to the end goal task, or like then you optimize it for all the tasks? It does better job. I mean,
do you get the question?
I'm not sure I quite got the.
So basically, let's say easiest example is like if one of the tasks that like you're doing, right, is the goal that you wanna basically accomplish, right?
Pre-training task is the same as the fine-tuning task.
Yeah.
Okay.
So if you just like do the training for that one task and then test it, right? Compared to when you train it for all the tasks and do so, how does it compare?
Yeah, that's a good point, but I think that kind
now sorry, to just like generalize this, basically if you have a similar task to one of those tasks, is it better to just like use that task to optimize it and then use it, or like it's better to add unrelated tasks? Not unrelated, but like
I think it totally depends on what you're evaluating on. The main one of the big points of these papers, these shared encoder papers, is that you want to avoid overfitting to one particular task, and so you want to create something that's going to generalize well to different tasks, but also different data sets. Like you might pre-train on one particular task on one particular data set, but then you might test on the same task but a different data set that has maybe different vocabulary or whatnot. And if you've only pre-trained on that one task, that one data set, you might not be setting up your shared encoder to perform as well. It's a valid question though, whether or not you perform better, but
yeah, if you have tasks that basically it's not represented in the literature, right? Someone is going to do some new task and they don't have the resources to train like a big network, right? Then it's good because like you have a model that works for everything almost. But like if you have something that you have similar tasks, right? Probably it's better to go find those models because they're already kind of doing the same job that you want to do, right? You don't want to use something more general, which is doing like so or so many tasks, but probably it's not the best for one task.
Something that I
just want to say that probably the question is more general than this, and that probably has been answered in the literature because multitask learning, of course, exists before this, right? And I was telling Rahel about all the examples before that are using not this, but just standard mathematical multi-objective optimization. So they combine word learning to text learning. And the example I was telling her was like, for example, for Wikipedia, you can have word similarity, you can have text similarity, you can have graph similarity, and they combine them and they show that sometimes it works better on each of those tasks, just because it generalizes better. So probably that question is at least more general than this paper. That's a more general question that does multitasking help or not.
And something that I also wanted to add to that is none of the pre-training tasks use supervised data. So you can't really, although you could, it's not enough data for you to learn the language representation, right? So all of them are like, a huge amount of data, but like you tweak them a little, or like you construct them in such a way that, like sentence reordering, for example, you construct them in such a way that they already sort of, you get weakly supervised label from a large amount of data. And then because you're doing this over and over again with respect to huge amount of data and across different tasks, the aim is that, you will eventually learn better representations. Yes.
Do you know if this actually happens like in your brain? Like, do you actually have shared weights for this, and then you diverge, like with transfer learning, or Is it just like the node, like your neurons, or is it just like this works? So that's great.
That's a very good question.
That's a good question. So basically, your neurons theoretically have access to each other, right? You can start some firing over here. You I don't know prefrontal lobe, and then go all the way. Physically, possibly, you can go all the way to your occipital lobe, right?
Yeah.
But there are inhibitors that would stop you. So the weights in your entire big cortical neural net would stop you from firing or reaching sort of remote areas. So I'd say, as a cognitive scientist, that this is more similar to brain than focusing on just one task and expecting it to do best.
Right. I guess like what I'm saying is I think when I'm reading a textbook, it's different than reading like Harry Potter. And I think I'd just be surprised how much is actually shared. Because this is a lot shared, right? Like obviously, like if you're using an encoder decoder network, I'm just curious. I don't know. I'm not cognitive science.
So I think trying to understand the point, you're saying that even reading different domains is represented differently, probably in my brain. Is that what?
Yeah, sort of. Like in the sense of like, as we're saying, like the surface is changing, but should we be even trying to compute all these tasks using, or you do all these tasks using the same, all the pre-training? Do you get what I'm saying, or is it just like this sort of mathematically works?
So I think the analogy towards brain would be then would we be using the exact same parts also in our brains while we're reading Harry Potter versus scientific textbooks?
Exactly. Yeah.
So probably not. I mean, I know there are EEG and fMRI, event-related fMRI studies that show that people, even with like there are a lot of studies trying to show even with subtle changes in the same task, people using different sort of small regions of the brain.
Yeah.
So I would say theoretically the same thing should be happening in the human brain, and therefore I think over here as well, like if you give it a different sentence, a different text or document, you should see a different firing pattern in your network, right? That's why because your tokens are represented differently. Right. So it's the same architecture, but use it differently. I'm not saying it's absolutely. If there was a neuroscientist in the room, they would hate me and kick me out right now.
One more thing I want to bring up before we wrap up. So in the circle at the beginning, I thought Max had an interesting point or question that I'd like to pose to everybody. So a big part of the contribution, as Royal mentioned in the paper, is this idea of being able to very easily, modularly add new tasks and not start from scratch. So I'd like to pose to you guys what Max was hinting at.
It's Andre, Max is over there.
Oh, I'm so sorry. Andre, of course. I'm getting so many names wrong. Thank you, Andre. So the question is, if you took a model like, let's say BERT, and you wanted to apply this same idea of adding a new task. So BERT is trained on masked language modeling and next sentence prediction. But let's say you decided you wanted to add an additional pre-training task to BERT. Would that be catastrophic to try and add that task in, or would that be something that you could adjust BERT to be able to do?
How are we defining catastrophic? Like it gets worse on all these tests?
I guess.
Yeah.
I would define it that you have
to
to
train with the second task and then go back test on the first task, and the results get worse. Random mess. Yeah.
Right.
Or as an engineer, you have to do so much more work that it is better to start from scratch.
Oh, I see what you're saying. The training would take just as long as if you added it from the beginning. That's what you're saying?
Or changing
like
the architecture, even changing the architecture. You have to.
Okay. Like basically, is this concept that Ernie is introducing, is it transferable to BERT in any way, or other models, or is it fundamentally unique to their architecture?
Is it a question?
That's the question.
Why would stop using BERT with this approach? Like, could you just give like batches from different data sets and just add the gradients and update the weights? Like, why wouldn't it work? Yeah, like that's my question.
I thought there is a lot of changes as compared
so,
to.
So what makes BERT is the way it was pre-trained, right? They use the same other architecture as BERT, but with different pre-training. So then, what do you mean when you say?
Yeah, like if you take the same transformer, you just train it differently for train.
Yeah, that's pretty much what everyone's doing.
It's not BERT anymore, right?
Yeah,
okay.
It's not. So that's what Roberta did, right? Okay. Roberta changed BERT's pre-training, and they call it Roberta.
Okay.
So.
Probably a practical question. Like, can we download this and like which platform they have used to develop this?
Paddle.
Use Paddle.
Library does not talk of TensorFlow that Baidu wrote for their own internal.
So what's the name?
Paddle.
Like a canoe paddle? Paddle.
Okay.
So probably most of us in the room are not as familiar, but
it's available. Like it's
open source.
Yeah. And the code for this paper, right?
It is. Everything is available. The code and then pre-trained model, everything.
Every file you see, import paddle.
The thing is that I went to the forums even, that because most of it is in Chinese, I couldn't understand the
documentation is a little
the documentation of paddle, I would say it's not very well documented for the English version.
But the GitHub repository for this thing is very well documented.
Sure.
Does it have Python?
Yeah.
Oh, it's all Python based.
The interface. Yeah, okay.
Yeah. Okay. It's completely in Python, but not deep learning, like not TensorFlow.
I don't think it's that different really. Like I haven't read that. But the code and the pre-trained model, everything is available.
Sorry, what did we say about if it was catastrophic or not? What's everyone's opinion? Did we get to a conclusion?
About?
I don't think
there was a
anyone
mention
answered
of
that
Roberta.
question. What?
There was a mention of Roberta the last part of this discussion.
What's the question about
what about catastrophic?
So they were saying like if we would do this with BERT and try to add on append on a new task, would it be catastrophic?
Right, we kind of ignored.
Yeah, the room went silent, and then we just like jumped.
I think that the architecture is very different.
Yeah.
Like yes, it is using BERT underneath, but it's very different. Like they have all these results that they added on top of. So I'm not sure if it's even fair. Like they have a shared representation. I'm not sure if it's directly comparable. Like how would you make sure? So let us remind. So for BERT, did they use it? Did they use the same architecture to tackle all the tasks, or?
There were two tasks.
Right.
And basically, the token level loss, you calculate like basically feed forward and softmax and cross entropy over the vocabulary. And there is this next sentence prediction, which is a binary, which you have the same feed forward, and I think that you use the CLS token to do that.
Right.
So in the at least in the PyTorch implementation of BERT, if you don't change anything and you have, let's say, thousands of data points, and for 500 of those you have two sentences, it only gets trained on 500. The reason is that it wants to train on both tasks at the same time. If you want to train on the other 500, which is single sentences, and you cannot have the next prediction task for that, you have to change the code to actually do mask language model on those. So basically, for each input sentence, you have both loss at the same time. By sentence, I mean sequence, which is basically.
So that's single task learning, right?
Pardon?
It's a single stage process.
Yes, it's a pre-trained version. Yes. So I'm saying that for BERT, like the data is shared between two tasks.
Yeah.
Well, that's too much to visualize and like to think about in my head. I'm still caught on the previous question that you asked. What if we start with different sequence of tasks, and would we still get the same result? And so I don't get to the catastrophe question. I'm still thinking about that, and I think it was still converge. I mean, with a different sequence of tasks. For example, if we
I think
and I don't think that would have a huge impact, because at the end of the day, the way it works, I guess it's just the way the weights are organized in the matrix. So if it works in some way, I think there would not be a huge difference between different sequences of tasks.
So let's answer this first. If we try to train vanilla BERT on this, what are we gonna have to change? So we have to change our cost function because you have different tasks now. And if we do that, can we leave the rest as is? And if we do that, what significant bit are we missing that they contribute to the performance? So I think if we answer these, then we can say if BERT would perform that, as a theoretically.
So is it even possible to do that? Because the kind of variation in the tasks is so huge that how would you ever do this with a BERT architecture? Like you can't pre-train on these many kinds of pre-training objectives with a BERT architecture, right? Because you're talking about sentence level and then combining that with token level.
So that's kind of what I was thinking, but I want others to also have a chance to comment. But I'm thinking like if you want to do that, then you end up doing this.
Exactly, it becomes Ernie.
Yeah, exactly.
Do the modification.
Yeah. I think it is much easier to do like without changing too many things. Just the way BERT does with for tasks that use the same data set. So I think in this like that should be much easier. And then if you have higher relation task and discourse task, then it eventually becomes Ernie.
In the end, it makes sense. It makes sense that these models are close because after all, it's Ernie and BERT.
Yeah.
Ernie and BERT. BERT and Ernie, they live together.
Didn't pay attention to the experiments. But like, let's say BERT is like, I don't know, bicycle. This one is like an airplane, bicycle, car, doing everything, right? Now, like, if you compare like how it's doing like the bicycle job for the task that like BERT is designed, right? Have they like compared these two?
Well, yeah, I mean the glue is the
it's doing better job than everything.
Yeah.
Well, yeah, I mean glue is the general. The idea is it's a general language benchmark with many different tasks. So the idea is not to just look at the task that, like the pre-training tasks for BERT, mask language model, next sentence prediction. These are not tasks that you see in the glue benchmark.
Yeah, that's what I'm saying, right?
But
if you do those two with this and then BERT and compare, I would imagine like probably the BERT is going to do a better job because it's designed for that.
On a downstream task of next sentence prediction. Perhaps, yeah.
Could you repeat the question?
So the question is, if your downstream task is mass language model or next sentence prediction, the pre-training tasks of BERT, would we expect BERT or Ernie to perform better?
Or at least it's a good thing to try because if you claim that you're doing a better job.
But
I think that's not the objective.
Because like
the value in having that.
Well, like it's not fair, basically, to compare like BERT, which is like for something that is not designed for, right? BERT doesn't claim that it's doing that blue thing, right?
It does. Sorry, it does.
Yeah.
So sorry. Yeah, we should refresh. The whole idea of BERT and all of these papers is you train on some pre-training tasks. Doesn't matter what they are, and then you're able to learn a general representation of the language such that that model can now be applied to other natural language tasks, downstream tasks, that are not necessarily the same thing. BERT never tried to make their pre-training, and in fact, it's more impressive if they're more different.
Right, yeah.
I see, but then, sorry, like, it's kind of like, I'm not convinced that then they have come up with something new, because like, of course, they have like more tasks, more data, and then, of course, you're gonna have a better result, right?
So I think what the paper's selling point is that their multitask approach claims to have a better language representation as compared to BERT because of the fact that you are giving it different.
The metric is glue. Right?
Yeah, and glue is a good benchmark because it actually looks not just at one kind of text classification. It looks at text, multiple kinds of text, textual tasks, right? So if you're comparing on the same downstream tasks, then it makes sense that these guys are saying that the results are better than BERT, and it's a fair comparison. I mean, in my opinion, it's a fair comparison.
Basically, like, it's experiment design, right? Like, you need to keep everything same and change one thing. Like, are they claiming that they have a better architecture, which they don't, right? Or like, I don't know, better.
Now you're just being mean to the author. So I think we fairly pointed out that like it's kind of tough to do the ablation. I mean, I would love to see ablation studies, and I think we should, but it's kind of tough to do it like at a granular level. Also, like to say that of course it would have been better. Like I think that's kind of like that's mean. Like because yeah, we would think so, right? So I'm glad to see that it like my intuition was also it would be better. But it's always good to see the experiments, and then move forward if that makes sense.
And I feel like that was the logical sequence of thinking too, that they thought, okay, BERT, and then we need to probably adding more task would improve the language representation. So they sort of changed the transform, like with the transformer, they designed an architecture that you can add more tasks, and because of that, you have to have more data, and it's just that I don't think you could have done it with any other models, and in some way, I mean, just slightly different.
I agree. This question is definitely still open. Like, how much did the data sets improve versus the new architecture and tasks? But nonetheless, I think, as Ehsan said earlier, it's still very much a valid and impressive paper. And just because, you can't say, well, of course, because they added new tasks, they did better. Obviously, their hypothesis was if we add new tasks, then we'll do better. But
down the road, they paid for 48 or at least 64 GPUs. When
yes.
they spend that money, probably.
With love and money.
I just want to add, every criticism he made about this paper should be applied to the Roberta paper, because that was just an abuse of everything. Like, it's the most disappointing paper I've ever read. Like, they use 10 times the computational power of BERT, they use 10 times the data set, they use 5 times the batch size, and they use 500 V100 GPUs. 500 V100 GPUs.
Did they beat this one?
They thrashed it.
Okay.
So like obviously that's going to beat everything, right?
I think I quickly wanted to also mention.
Someone online said that too.
Okay.
Quickly wanted to come back to the question that
no
you were asked
to any architecture.
Oh yeah.
about different sequences, right? So something that we recently came across, I think, was it Richard Soccer?
Yeah.
So something that he meant. This is an ongoing research, I think. So they try a slightly different approach. They call it anti-curriculum, I think, where you begin with the hardest task and then you slowly progress to easier tasks, and then that performs better in their approach. In the experiments
as compared to with the curriculum learning?
with the curriculum.
So what's it called?
Anti-curriculum. The like
anti-curriculum.
Yeah.
Curriculum.
They did it on declinal feed, however.
So it probably has improvements too if you begin with the harder task and then move on to a slower task.
Curriculum when you start with the easiest one and go to the hardest one. That's
Yes.
curriculum. Okay.
I think we should probably. There's been a great discussion. We should probably wrap up.
There one comment over there.
Me?
Yeah. Did you
Oh
have
yeah. I was just curious. Like when they do these downsheet tasks, in terms of comparing these two papers to BERT to this paper or XLNet, whatever you want, is the same architecture for that?
For the fine tuning layers?
Yeah. Like do you know what I mean? Is the network different then?
Oh, good question. I'm not sure because they mentioned that.
Because if it was different, then yeah, I can't make any deductions. That's
You mean the task specific part of
Yeah,
it?
like the
Fine
tuning layers that they're running on top of.
Okay, we might be wrong, but our guess is that they use the same. If you have one layer or two layers of feed forward, it's the same across different tasks.
Yeah.
However, because you are predicting different number of classes, at the end your softmax is predicting.
No, it's not. Well, I'm saying as the glue. So like
For BERT, is it the same?
is it the same from going from this encoder decoder? Is it the same amount of I don't know layers, whatever you want to like the width of it? If you know what I mean? Did they change that as well?
Oh, okay.
Compared to BERT.
Yes, exactly. Because then if they didn't change it, they kept it the same. Then we can say, okay, this pre-training was better, arguably.
Yeah.
And then if they did, then it's like, well, which one's better? Which one influences?
We know that in BERT is feed forward plus softmax, but they didn't specifically mention what is the layer, the task specific layer here.
I mean, we can look at it.
I think if it's fair, then we should assume that it's the same, but there is no
Very likely it's the same. I mean, if they took so much effort to make the BERT large model like setting, they probably would have thought about.
That's a good question, though.
Yeah, it's good because I saw that the pre-training was the same in terms of the network amount of stuff.
Yeah.
So thank you so much to everybody. It was a really nice discussion, and thanks to Royal and
Thank you for coming.